Oh, thank you. Well, good morning. I'm delighted to be here, of course, to tell you the story of the universe and the story of how we found out about it, and to try to explain why people stood up and plotted for that simple curve that Per described. So I'm just thrilled to be here, and our entire team that worked on this project is thrilled to be here to share in the recognition that our work was as important as people now in the professional astronomy world have known for so long. So here's our quotation from what the Academy has said of our work, and I need to explain to you what these terms mean as we go through the presentation. So first I wanted to explain how it is that astronomers know about the universe. You will say, how can you know about the early universe when you're not there? And the answer is that you can look back in time by looking at things that are very far away. Light travels very rapidly, but speed is not infinity. So when you look at your hand, you see it as it was 3 nanoseconds ago. And when you look at the sun, you see it as it was 500 seconds ago. If you look at the middle of our galaxy, it's as it was 25,000 years ago. And if you look to the most distant things that we can see, this is an old chart, as you can tell, we know how they were about 15 billion years ago. Our current number is 13.7 billion. So look far away and you can look back in time. It's a little bit like geologists looking at old rocks, but ours is a little done with a different technique. So how do we know how far away things are? That tells you how back you're looking in time. Well, we have the two basic methods. So one is the high school trigonometry method. You make triangles, and we depend on the fact that the Earth moves around the sun to give us some parts of the triangle. So we can measure distances to stars that are nearby. To reach to distances that are greater, we need to use the comparison of brightnesses of different objects. And so if you have two candles that are equally bright, then you can calculate the ratio of distances between them by this very simple formula that is here. Now, a very large fraction of the effort of astronomers over many years has been into understanding how bright things really are, so that when we say that something is fainter because it's further away, we really know that it's because it's the same kind of object that we know nearby. So second thing we need to know to understand how the universe is going is to tell how fast things are moving. Well, a few things move across the sky, and you can say, well, I see that. When you see a small satellite moving across the sky at night, you can tell. But when things are far away, you can't do that. They don't seem to move across the sky at all. So all you can do is tell whether they're moving towards you or away from you. And nature has given us a way to do this. The color of light that we receive from distant objects is seen to be redder than it would have been if the object were close. And so this is a clue that the universe is expanding. The wavelength changes due to the relative velocities of the Earth and the distant object. So nature gave us some little markers, which we call atomic spectrum lines, and they can be seen when you spread out the light of the sun or a star with a prism. So we have these very characteristic markers that nature has given us. We can be very precise about this. So back in 1929, when the worldwide economy collapsed, we also discovered that the universe is expanding. So this is Edwin Hubble's plot from 1929. And if you divide the distance that he estimated by the velocity, you determine the apparent age of the universe. And the remarkable thing about his plot is that all of the objects that he measured seem to be consistent with a single age for the universe. The distance away is just proportional. The velocity is proportional to the distance. And a very astonishing conclusion that can be drawn from this is that there is no apparent center or edge of the universe. No direction is preferred over any other direction, and we calculate that no particular observer is privileged either. So even though it looks like the entire universe is receding from us, we calculate that an astronomer on another star, another planet around another star, far from here would also conclude that he was at the center of the universe, or she was at the center of the universe. The conclusion is, well, none of us are at the center of the universe. So maybe the universe is even infinite in size. So this was something you could immediately calculate from this chart. As it turned out, the prediction had already been made in 1927 that this was possible. Georges Lemaitre, who was a Belgian priest, was able to calculate from Einstein's equations that the universe might be expanding. So I have some pictures of some of the major contributors to this work. Georges Lemaitre is shown there with Albert Einstein. Now, Albert Einstein had denied that the universe could be expanding, and he said, no, that's impossible. He was very rude to Georges Lemaitre, but after the evidence came in from Edwin Hubble, it was pretty clear that the universe was expanding. He was quite apologetic at that point. Later on, in the 1940s, George Gamow was a professor at the George Washington University in Washington, D.C., and he had two students, Ralph Alpher and Robert Herman, who were graduate students with him, and they started thinking about the consequences of this Big Bang. And they said, well, okay, it was very hot. And they were interested in what the content of the universe would be from this picture. And you can calculate there should be hydrogen and helium and heat radiation. So they did that calculation, and they said the universe should have the amount of radiation in it which was equivalent to about 5 degrees Kelvin, 5 degrees above absolute zero. Very cold, but nevertheless an immense amount of radiation. This is the radiation is left over from the Big Bang itself. I have pictures of two more recent theoretical physicists here who have given us much to test and think about in the early universe. Jim Peebles I have here, among other things, because he's written what we consider practically to be the Bible of cosmology. It's a book this thick, and every word you should read. It's great airplane reading. Now here is a picture from 1965 that gives the understanding of the universe immediately after the Big Bang radiation was discovered. Penzias and Wilson discovered this with their equipment at Bell Telephone Laboratories, and the competing team at Princeton of Dickey, Peebles, Roll, and Wilkinson were working on the theoretical predictions, and shortly after as well confirmed the measurements. So this is the picture they gave us, that there is a, in this square we see several curves. Temperature of the universe is sketched on the vertical axis, and that applies to this lower curve here. And it shows how the universe expands, ranging from the very earliest times when the universe was very small to the present time. This is now. Here the age of the universe in seconds, so this is 13 billion years here, and going back to sub-second, early milliseconds. Now in truth, this chart can be drawn many orders of magnitude over this way, but they didn't draw that because there wasn't much to say yet. So as the universe expanded, the temperature fell. The temperature and the size of the universe are inversely proportional. So this is a straight line. The density of the radiation, that's rho sub r, falls off as the fourth power of the temperature. And the density of matter, which is this curve, falls off a little more slowly. So this summary chart here was the one that we used to explain to NASA and many other people why our project needed to happen. So we wanted to find out everything you could know about this chart. So I wanted to point out a couple of things on here. Here is when the universe is about 1 year old. And this is when radiation is still dominant over matter, but we calculate that the color of the radiation from the Big Bang is established around this time. Another point over here is when the transition from matter-filled to radiation-filled universe occurs. It just happens to be about the same time that the universe became transparent, and which is marked here, where suddenly the heat radiation was able to propagate directly to us. So we see it as it was at that time. So this was, excuse me, this was the chart we needed to explain why we needed to measure better. So now let me set you a picture what was science like, physics like in 1970 when we started work, and I was a graduate student looking for a thesis project. In 1965, which was only 5 years before that, the cosmic microwave background radiation was discovered and announced and confirmed. So, but 5 years later, a few more measurements had been made, and it appeared that everything was wrong about this picture. There was 50 times as much energy measured at shorter wavelengths as there should have been. Other measurements were suggesting there was a problem. There was even a hint that there was a spectrum line in the cosmic background radiation, which would have challenged the entire story of what it was. So all of these things made people very nervous. So a whole series of projects were done in many laboratories around the country and around the world. But this is a particular group that started work at Berkeley. Paul Richards was my thesis advisor. Mike Werner was a young postdoc when I was working with them. And we started a project which we took up to the top of a mountain. And David Woody joined us shortly afterwards to build a balloon project. In those days, we used vacuum tubes. Many people may have never seen a vacuum tube these days, but that was all we had in those days. A very tremendously important mathematical discovery was just made at that time called the fast Fourier transform. It's now something that's implemented in little bits of silicon and is part of almost every communications equipment. We didn't have pocket calculators, and an advanced laboratory computer used paper tape for putting the program in. And we made our infrared detectors with soldering irons and tweezers, which is not the way that we do it anymore. So I wanted to show you pictures of my friends and competitors. This is Paul Richards, my thesis advisor. Mike Werner, I mentioned. He is now my counterpart as the head scientist for the Spitzer infrared telescope at Jet Propulsion Lab. Here is David Woody, my fellow graduate student. Frank Lowe here has been widely recognized as one of the fathers of infrared astronomy, partly because he invented these kinds of detectors that we used, as well as many other kinds of equipment that we did. Herb Gush was at the University of British Columbia, and he was a competitor for us. He was building a rocket payload, and he was doing very well with it, but had bad luck about the rockets, so he didn't quite get there first. Ray Weiss started up a series of balloon payloads at MIT to measure the spectrum of the background radiation. And he wasn't the only one. He was a competitor for my thesis work, but shortly after became one of the initiators of the COBE satellite. Now here is a sketch of the instrument that we built at Berkeley. This was my thesis project, and this was a balloon payload, and this is a very simplified sketch of the apparatus. Anyway, light came down from the sky, was bounced around through this conical antenna, and went into something called a Michelson interferometer to measure the spectrum. And by the way, Albert Michelson got the Nobel Prize for his work on interferometers and other things in 1907. So our technology, or at least our basic concept, is extremely old, but the application is very new. This is Paul giving the apparatus to the Air and Space Museum in Washington, D.C. So you can see it. It's quite startling to go visit your own apparatus in the museum. It makes you feel old. So anyway, how did the project get started that we're going to describe? The COBE satellite came from a competition that was announced by NASA in 1974. They received about 150 proposals, and in that group were three. One was from Jet Propulsion Laboratory, and Sam Gulkas and Mike Jansen were leading that. One was from Berkeley. Louis Alvarez, who's a Nobel Prize winner in another subject, was the official leader, and George Smoot was the young man who actually was leading that, and so he's here to tell you why this was important. I organized a team here, and this was our team. We led this proposal and submitted it from Goddard. So here are pictures of the people. Pat Thaddeus was my postdoctoral advisor. I was 28 years old when we did this, and so he was the guy who said, well, go ahead, you could do that. I've shown pictures of spouses here because I wanted to emphasize that this has been a very much of a lifetime occupation, and every person's family was an essential part of this project. So these are the team members who were chosen by NASA headquarters to lead a new study team in 1976. So here they are. This is the next step of history. In 1976, Nancy Boggess, who was our program scientist at NASA headquarters at that time, chose 6 members. And we chose the 3 principal investigators as well. Around 1979, it was decided this observatory would be built in-house at Goddard Space Flight Center by the engineers there. And so this was a tremendous step forward because It enabled the scientists and the engineers to work daily together. We could go argue. I could wreck their equipment any day. In 1982, it was approved that we would build this project, but then in 1986, the Challenger space shuttle exploded, and we had to redesign the entire project because it was supposed to be launched on a space shuttle. It was somewhat of a miraculous thing because we had to lose half the weight of this original design in order to get it onto a Delta rocket. But it was possible, and our engineering team found a way. So 3 years later, we launched this mission November 18th, so it's now 17 years ago. It took only a few weeks before we showed the spectrum that Per described to you, and a couple of more years after that before we could get the first discovery of the hot and cold spots that George will tell you about. So here are other members of the COBE science team. Chuck Bennett was the deputy principal investigator for the microwave radiometers. Here's Nancy with her husband Al. Ed Cheng, Ellie Dweck, one of our theoretical astronomers. Tom Kelsall, deputy for the infrared background experiment. And Phil Lubin. And more members of the team here. Every one of these people had a special role. I should point out especially Ned Wright, who I think was the first person to see the cosmic background bumps that became so famous later. So what did we do? These were the official roles of our project members. And so I'll show you a little bit more about what we did. But one of the lovely things about our team was that we were all co-investigators on all of the instruments. So we all participated in the arguing and deciding what it meant. Here are part of our engineering team. There are actually many hundreds of engineers working, and the total team was about 1,600 people. But a few special people I'm pointing out here. Here's Roger Mattson, who is our project manager. And on the next chart, our deputy project manager, Dennis McCarthy, here in the back row. So these are just a small number of the huge team that it really took to do this job. Here is what the satellite looked like in orbit, except of course the sunlight was not have been shining on the instrument package inside. This is artist's concept. This bird was 900 kilometers above the Earth, orbiting around the Earth in what's called a polar orbit, so that it was orbiting over the sun, the daytime-nighttime boundary of over the Earth. And that's a place where we were able to keep the sun out of the apparatus at the top and shining on the solar panels from the side all the time. So it was a lovely orbit, and we were fortunate in nature it gave us this possibility. So now I'll show you the apparatus that we used to measure the far infrared spectrum of the Big Bang radiation. So here you'll recognize this as very similar to the balloon payload concept that I showed you before. Here the radiation comes down from the sky, bounces through a conical device and into an apparatus where there are beam splitters, moving mirrors, and radiation that goes out to the detectors. This one's a little bit more precisely designed, but an important factor here is we now have a Big Bang simulator. The prediction of the Big Bang radiation is that it was basically an equilibrium form of radiation, which leads to a very unique spectrum prediction, in which there's only one number that's adjustable, and that's the temperature. So our idea here is we'll make a perfect simulator of the Big Bang, have it adjustable in temperature, so that when you put this device into the antenna and replace the sky, if you get the same answer, then the sky has the same spectrum as this calibrator. So that was our strategy, and we were able to do it extremely well. That's how it was that even only a few weeks after the launch, we were able to immediately draw the chart that people were so proud of. So here's this calibrator body magnified as much as I could. Before it's been all properly insulated, you can see it's black plastic. And here is the little protective point which we had to make sure we got off before we sealed it up and put it in the cryostat. Here's the black and conical metal antenna that's used to receive the light. So here is the chart that Per described showing the Big Bang radiation. This is this theoretical curve, and the little boxes show the data points that we had. We didn't even know how precise they were. We just assumed it was 1% in order to be able to draw the chart. But all of the points lie exactly on the curve. So this was the thing that people recognized as so important, and why was it so important to us? Well, I think the number one thing is that people had been a little worried that the Big Bang was not the right story. There were so many measurements that were a little fuzzy about what the right brightness was. That not very long before there had been measurements, including measurements by our group, that showed there was a little bit too much radiation out here. And if that were true, then the whole deal was off. The Big Bang could not have been the whole story. So I'll show you a little bit more about what this meant and how we got it. Just to tell you how we made this processing, we had to sort all the tremendous amount of data out, and we had to take out something that's turned out to be a useful effect for other people. Cosmic rays hit the detector, and they make little bumps of temperature, and though you have to find all those and take them out, then we had to make a simultaneous least squares fit, which is basically a model of the sky and a model of the instrument, and adjust it all to fit the data. And Dale Fixon led that team, and it was a huge effort. Anyway, we make the maps, then we take out our understanding of everything else that's going on. The sky is full of dust in between the stars, and atoms and molecules between the stars, dust in the space between the planets. There's some kind of far infrared background radiation from other galaxies, and there's a small effect of the motion of the Earth through the universe. And all of these things we have to understand and remove and see if there's anything left that would worry us about the Big Bang. And the answer is nothing was wrong. So here is a plot in terms of temperature units. Our final estimate, our best and final answer is 2.725 degrees Kelvin, plus or minus only 1,000th of a degree Kelvin. So this is one of the most precise temperature measurements that exists, and is traceable to the Bureau of Standards, of course. Right now we call it NIST. Anyway, the deviations from the black body form are extremely small, less than 50 parts per million of the peak intensity. Now, if we felt that there was a necessity, we now think that new technology could do this even better, but so far we've not been required to do it. Now, here are a few formulas just to illustrate that we can write very elaborate papers. There are two forms of change of the spectrum that could have occurred, depending on when the universe was busy doing something that we didn't expect. And so in this particular, what we call redshift range, which is between the first year and the first 1,000 years, roughly, it would have been possible to have this form of a black body radiation instead of having this little number mu be 0. So we had to go measure how far could mu be different from 0. And later on, we could have had a different form of spectrum distortion between the first 1,000 years and basically a few 100,000 years. We might have seen also a change, and we also didn't see anything there. So to summarize all of this, numerically, we have that the background radiation matches the Big Bang prediction. Within 50 parts per million, we have its temperature. We have these numerical measures of how much distortion there could have been. And now we have a lot of interpretation. It basically says that only 1/100% of the energy of the cosmic microwave background radiation that we have now could have been due to any other source. And we had a long list of things that we thought might have changed it. So none of those apparently happened. And the other thing that people cared a tremendous amount about was the hot Big Bang story seems to be the right story. Had this not been true, people would have been extremely worried. There were other theories people had in mind. There was something called the steady state theory, which was popular until the discovery of the background radiation itself. When the big background radiation was discovered, people still thought, well, maybe there's a way that a steady state universe, which is continually being replenished with the creation of new matter, might have still been able to generate a cosmic microwave background radiation. But what it couldn't do easily was to explain why that radiation would have such a perfect spectrum of the Big Bang that we have, because complicated astronomy hardly ever produces simple results. So Ellie Dweck, who's a member of our science team, is also a cartoonist, so this is his take on this. It's been pointed out that neither of these gentlemen is a lady, but nevertheless, I should go on. We did find out a few other things about the universe. Number one, we wanted to see whether there was something else in the universe going on besides the microwaves. So we were able to measure an excess radiation called the far infrared background radiation that comes probably from galaxies of a new type that hadn't been known before. This was actually measured first with another instrument on the COBE that I'll show you briefly. We measured the far infrared radiation of the interplanetary dust, which had never been seen before. We were able to confirm that the difference in brightness of the sky due to the fact that the Earth is moving through the radiation has all of the right behavior to be due to the cosmos as well. We were able to check that nothing's funny about this change of the spectrum with direction. We found out that there's dust in our universe, in the Milky Way. Of course, we knew that, but we're able to give a great deal of information about it. We discovered an atomic line that had never been measured before. We mapped the molecules and atoms in our own galaxy. And finally, not that we worked on this very hard, we basically assumed that Planck was right about his formula. But if it hadn't been true, our calculations wouldn't have worked. So just to point out, this is not a new subject. 2 Nobel Prizes were previously given for work on this very subject of the blackbody radiation itself, not to speak of Penzias and Wilson's prize for discovering the microwave background radiation. I want to speak briefly about another instrument, which was called the diffuse infrared background experiment, and it was part of its job was to confirm that the microwave radiation was what it seemed to be, and part of it was to look for anything else that was interesting from the early universe, and it did indeed find something. So I'm not going to tell you a lot about it, but I just want to show you a simplified optical diagram. Here's the light coming down from the sky. This telescope is a small one. The aperture is 20 centimeters, but it's a very carefully designed one to enabled us to get what's called absolutely calibrated data, which is to say we know exactly what it measured. And here are the cosmological results that it got. The universe has produced 2 kinds of infrared radiation that are due to things that we hadn't known about before. One is near-infrared wavelengths, which is just a little bit longer than visible light, and one is at far-infrared wavelengths. And each of these has a brightness that is at least comparable to the amount of luminosity of all the galaxies and stars that we ever knew about before. So the total result is that the universe is twice as bright as we had known. And an important result of this, however, is that there's nothing the matter with the Big Bang. There's nothing out there that does not belong to these far infrared and visible galaxies. So to wrap up, I want to say a few words about what's coming next for me. This is the James Webb Space Telescope, for which I'm now the senior project scientist, and we'll be using this to reach back farther in time than we have with other telescopes, and to check out many of the things that we want to know about the early universe. So this is a current project of NASA with European, Canadian, and Canadian space agencies. Our prime contractor is Northrop Grumman, which has a main laboratory near Los Angeles Airport. We have 4 instruments on board coming from Arizona, European Space Agency, Jet Propulsion Lab with European Space Agency, and from Canada. And the telescope is going to be operated like the Hubble Space Telescope is done at the Space Telescope Science Institute in Baltimore. This telescope is 6.5 meters across the mirror, which is way bigger than the rocket, as well as being way bigger than any other telescope we've ever had in space. The Hubble Space Telescope is about 2.4 meters in size, so it's a lot smaller. This telescope is going to also be 1 million miles away from the Earth, 1.5 million kilometers, orbiting around a place called the Sun-Earth Lagrange point. So it's not possible to repair it, but we have to get it right the first time. So this shows that the observatory will be protected by a sunshade, a giant umbrella that's approximately as big as a singles tennis court. All of this is going to be folded up inside the rocket, and I call it the origami telescope. The process of unfolding this is something which is a tremendous challenge for mechanical engineering. And for some mechanical engineers, it's a great challenge. For others, it's a terrifying prospect. But we do believe this is possible, and we have been doing the necessary tests to demonstrate that this will all work. And we are going through this process. The observatory will have this deployable infrared telescope. The mirror here is made out of 18 beryllium segments, and unlike the Hubble Space Telescope, they will all be adjustable so that we can get the mirror shape correct after launch. It's the only way we could possibly build a telescope this big, because it's not possible even in principle to make a rigid, stiff, perfect telescope that will stay in shape, especially if you're going to have to unfold it. So the plan is that this will operate at a temperature of about 40 degrees Kelvin, which is way, way below room temperature, so that it does not emit infrared radiation that contaminates the measurements. It will operate for about 5 years at least, and the goal is for 10. There are 4 main themes we think scientists will use this observatory for. One is to pursue the discoveries of the distant universe. We now have what we believe is an accurate picture of the content of the early universe. We have dark matter, dark energy, which causes the universe to accelerate the expansion, and ordinary matter. And we have maps, which George will show you shortly, of where all of this matter was when the universe was young. We now claim that we should be able to calculate how everything turned into stars and galaxies. So we want to go see if any of that is true. So we'll take pictures of the early universe, identify the little faint fuzzy specks that seem to be from those most distant parts, and analyze the heck out of them. We'd like to see how galaxies like our own were formed, because we have the opinion that galaxies were formed from small parts that have joined together to make big parts. If this is true, we should be able to see that the early galaxies are quite different from modern galaxies. We would like to be able to see stars being born. We already know that this is happening, and here's a picture of one where this is happening. This is something called propelid. This is a luminous background of glowing gas in the constellation of Orion, and here's a dust cloud, a black cloud, absorbing the light from behind. And then in the middle of this cloud is a star, a young star, which is just beginning to turn on inside this dust cloud. So there's a possibility that there might even be planets forming in that little dust cloud, and in a few places we know where to look. There are a few nearby stars for which we have already observed that there are dust clouds orbiting around them, and we calculate that there could be planets there. This particular cloud, for instance, has a ring shape. You can quite clearly see in the picture. That ring shape probably occurs because there's a planet organizing the gravitational forces here to make a ring. And so if this is true, we should even know roughly where to find such a planet in this picture. So large planets, like Jupiter size, could be detectable directly by this new observatory. So there's a tremendous amount that's in our future for direct observation of the early universe, and for checking out our entire history of how we got here. So that concludes the scientific part of my talk. I just wanted to say, on behalf of the whole COBE science team and engineering team, that we are thrilled that our work has been recognized, and well, our most strong thanks that we could possibly imagine to the Swedish Academy and to the Nobel Foundation for this recognition. So let me conclude here, and thank you very much for your attention.